Good evening, my name is Chad Gardner. I will be currently doing the video for my group number 5, for our ENGI 1331 Project 2. In this project, we'll be covering two problems. The first problem is linear systems, in which we will be analyzing a system of equations and using MATLAB as a tool in order to compute these equations, and also whereby we're using user-defined functions in order to perform such tasks. The second problem will be what we have right here is numerical analysis, in whereby we'll be using an equation known as the bisection method, known as the bisection method, in which we'll use this method in order to analyze the maximum errors and also differences between roots. The bisection method is a pretty interesting method. These are methods, and also along with the linear systems, in which these are situations whereby these methods will definitely come across as engineering majors, depending on whatever course level. It could be further beyond, even in the engineering world. It's apparent that we'll come across stuff like this, and it's pretty much an integral part of us pretty much being able to understand them and being able to use them when necessary. As I said earlier, my group number 5, that consists of Micah Greer, myself, Chad Gardner, and Marek Matus. Purpose of this project is to, as I was saying earlier, is to use MATLAB as a tool in which we'll try to compute a solution to a system of equations by not only using user-defined functions, but being able to demonstrate an understanding of MATLAB operations. For our first problem, as you can see, there will be a scenario where we're asking the user to input a matrix, and right here to my right I have a function known as uptry, in which the uptry function is basically set up in such a way where it will compute the matrix submitted by the user and turn it into an upper triangular form. So there are two triangular forms, the lower and upper. But in this case, based on our problem, we were asked to have it done in an upper triangular form. Now, as an engineering student and reaching this level in this class, there are some functions that you can use without having to use, for example, a nested for loops like what we did right here. I believe one of the functions is called a triu, T-R-I-U, but in this case, because we're good students, we wanted to implement aspects of our understanding and learning in class to where we can apply it here and do it forefront. Then we have right here another function, which is the back sub function, excuse me, in which we'll be returning back that matrix that the user implemented by deleting the last column from the original matrix and performing it by bringing in the exact values as of before. Then as I go back to the group code here, as you can see, this is for our problem 1, as I was saying earlier, which we have our data validation to make sure to verify that the user enters a proper matrix, and where it allows the user to enter another data set matrix after they have entered the correct information. As we go on to problem 2, problem 2 delves into numerical analysis, and in this problem we'll be asking the user to enter a polynomial in the form of a vector. So in this case, the user will enter a vector with a list of numbers, and it won't display out as a polynomial, but we will have two functions that will be set in order to check analyze and also calculate the root approximations, the errors, and differences. Excuse me. Got a little bit under the weather there. So we were asked to construct two functions. We have a bisect root function, which we have here, in which we go into detail in calculating it, and form where we have a while loop in which we'll be asked again in order to run it. And right here we have a bisect root 2 function, in which this function would allow for us to find the difference between the roots, and while the first root function is set up in such a way where it allows us to find the maximum error. After having done these functions, we will then go back to our group code, in which, having asked the user to enter a polynomial in the form of a vector, we will then display out a graph. In the graph, we will be basically showing the number of iterations, in which this will display pretty much the maximum errors that the user had inputted, and also the differences, in which we will be pretty much have it displayed on a proper graph to give you a better understanding. Even though the data will not be exact, the graphs in this case will be best fit to give kind of an in-depth detail of what it's about. So as I'll go back to our first problem, based on linear systems, I'll go ahead and process the code. So I'll go ahead and run our code, and as you can see right here, it's asking the user to enter a matrix in the form n plus 1. So what this is stating is n is the number of rows, of course, and n plus 1 is the number of rows added to 1, pretty much saying that the n plus 1, which would be the columns. So if there's a case where you have a matrix that has 3 rows, in order for this program to run and efficiently, you have to have 4 columns. If there's a case where we have 3 rows, 3 columns, the code is set in such a way where it will ask the user to enter the correct matrix again. So I'll go ahead and show that to you. So I'll go ahead and say, for example, a 3 by 3. So we got that right there. We got 5, sorry, 7, 8, we have 9, 0, 1. As you can see, this message pops out asking to enter a proper matrix in the form. So I'll go ahead and enter a proper matrix of a test case that we had done, me and my group. So let me go ahead and do that for you. So as you can see, the matrix displayed is now in upper triangular form. And with our back sub completed, as you can see, we have x1, x2, and x3, the values displayed there. As I was explaining earlier, the upper triangular form is pretty much a diagonal. I didn't quite go in depth, but I'll definitely go in depth here. So it's a diagonal in which the operation is performed in order to preserve the shape of the original matrix. So as you can see, the dimensions is still the same, 3 by 4, but in this case, the first row is kept intact, and the second row and third row, the first sets of values are replaced with zeros. So this displays the upper triangular form. It would be the opposite way if it were to be the lower triangular form. As you can see, the menu is still running, the code is still running, so it's asking if you want to enter another matrix, which you will not. as we will go into problem 2. So problem 2, as I was saying earlier, talks about the bisection method, which will definitely be an integral part to engineering studies. And so you can see right here, as we have our code set together, we have our data validation, and after our data validation, which we go into our plots. So I'll go ahead and clear the command window and go ahead and run. As you can see, as it asks the user to enter a polynomial in the form of a vector. So go ahead and enter any polynomial. So go ahead with the test case that we used. So I'll put 3, 14, 26, 1. And then I will go ahead and enter the maximum error. So maximum error, I would say we'll go with 0.0001. Sorry. And the lower bound has to be a negative value. And in other words, in this case with the bisection method, as I'll go into more details about it, one of the first numerical methods to be developed to find the root of a nonlinear equation. It's an equation which, for example, f of x equals 0, where f of x is a real continuous function and has at least one root which is negative and one root which is positive in order for it to work. So in this case, I'll put like a -1, and let me raise this up a bit. Put like for a higher bound, a +1. So as you can see, our root approximation is, let me move these to the side, our graphs. Root approximation is our -0.039284. Our maximum approximation is 0.0002. And the number of iterations is 17. As you can see, while the data is not exact, the graph best fits is similar enough to prove the theorem is being true, as displayed here. So this is our first graph that we had displayed, which displays the maximum error per iteration graph. As you can see, it has a trend going where it's decreasing downward, exponential polyfit. So where we have the number of iterations and the maximum error. And then our second graph displays on the y-axis the difference between the roots and the number of iterations. And the difference per iterations that's displayed here. So let me go ahead and close these. Okay. Let me stop this. Okay. So as you see right there, that pretty much goes into details about the problem 2 of numerical analysis about our project. And that's it for my video. And do take care. Thank you.